Well, it's our pleasure to have Maria Yakerson from ETH to give the next talk, Universality of Algebraic.
Thank you very much for the invitation to the organizers, and also thank you for existing. I think pandemic is a good time to realize how much you get to miss your colleagues if you don't see them anymore. So that's the case. I will talk about joint work with Marc Hoyois, Joachim Jelisiejew, Denis Nardin, and Burt Totaro. And also the main results are based on a separate work of Tom Bachmann, recent. So we've been working on the update to our paper, and it's finally ready. So next week it will be on arXiv. And today I'll tell you about some of things you probably already heard me speaking, then I apologize, but in the end I hope to say something new, unless you were at the MIT talk. Okay, so let's see. So the goal for today is to understand a new universal property of algebraic Ktheory and some of its applications. So let me start with a short introduction. So in this talk, K will be a perfect base field. And when I say algebraic Ktheory, I mean a presheaf from smooth schemes over K to spaces. So Thomas-Trobot Ktheory, if you want, which can be defined in the shortest way as the following thing. So you can take the groupoid of vector bundles. It's an infinity space via the direct sum operation, so a monoid in spaces via direct sum of vector bundles. So you can apply group completion to make it a group-like infinity space, and this would be the right thing on affines, but in general, you can Zariski-Schiffify it, and you get the Ktheory. Okay, so so here. So vect is a presheaf of groupoids or SAC. So which sends T to groupoid of vector bundles over T, where T is a okay. So this is tricks. Okay, good. So that's how Ktheory can be defined. And then, well, okay, it's a great invariant. It has lots of wonderful properties. Let me list some of them. Okay, so some features. Of K, which I will quickly recall. So first of all, as if we consider it only on smooth schemes over K, it is a one invariant. And secondly, so we defined it as a Zariski sheaf, but it's actually has Nisnevich descent, so a stronger kind of descent. Okay, so these are two properties. And so in general, since we will be talking about material cohomology theory, we will work with localizations with respect to Nisnevich descent and A1 invariance. So when I consider, let's see, so when I localize with respect to A1 invariance, and I want to say that things are equal, this will be, I will be calling it A1 equivalent. And if I want to localize with both of these conditions, then I will call this motivic equivalent. Okay, but back to Ktheory. So it also, thanks to Bott periodicity, happens to be an infinite P1 loop space. And so it And the last thing that I want to mention is that it has transfers along finite flat maps, which, so just finite flat transfers, by which I mean that if I have a finite flat map of schemes, then since on vector bundles you can push forward along finite flat maps, you can also do that in Ktheory. So you have push forward. Although a priori it's just a pre-sheaf, so a priori it's only contravariant, but we have this covariance, which will be important. And so the moral for today is that I want to argue that Ktheory is in some sense universal among so pre-sheaves of spaces on smooth K-schemes with this, well, let me call them features, because the first two of them are actually properties and the 3 and 4 is data. So it's a mixture of properties and data, so let me call it features. And in 5 minutes, I will give a precise formulation, but this is the main idea. Are there any questions yet? Or so this was a vague explanation of where I want to argue, or what I want to argue. Okay, if there are questions, please interrupt me and ask. So to give a precise, yeah, Tony? No?
Well, I have a stupid question maybe, yeah. But so does motivic cohomology also have these transfers? Because
yes, yeah, they have stronger transfers.
Okay.
Transfers.
So this gives some sort of map from Ktheory to motivic cohomology then?
Yeah, well, not quite. So from the you'll see. From the,
okay, thanks.
From the like effective spectrum, like connective spectrum corresponding. So like from the Ktheory space, not the K2, but you'll see. Okay, so to make this more precise, let me recall that the stable motivic homotopy category of K is defined as P1 spectra in A1 invariant Nisnevich sheaves of spaces. On smooth K-schemes. So our Ktheory will give an example. But to give a precise formulation, I need to define a new category, which I will call SH finite flat, which is you do the same thing. So again, consider P1 spectra in the same kind of sheaves, but instead of taking smooth schemes here, you take a category of spans on the category of spans, which I'll call finite flat correspondences. So this category, it's a 2-1 category whose objects are again smooth K-schemes, but it has more interesting morphisms. So a map from X to Y is given by a span like that, and where F is finite flat, and Z is arbitrary scheme. Okay, so that's a map from X to Y. So they form a groupoid, and you can compose via taking pullback. Okay, so when you consider take pre-sheaves or sheaves on this category, you encode intrinsically the structure of transfers along finite flat maps, because having a map backwards along this diagram means that you can go back along any morphism and push forward along finite flat. Okay, so this is where so generalized cohomology theories with finite flat transfers naturally live. And our last hero is what Tony asked about. What I want to associate to K-theory is the so little KGL, which is the P1 connective spectrum representing K-theory. So the very effective K-theory spectrum. So it's the spectrum corresponding to our K-theory space. Which Tony does have a canonical map to material.
Is that?
I have another stupid
K-theory spectrum, or is that different?
One sec. So I mean, so let me. I think I'll answer now. In a sec. So under the complex realization, this goes to something maybe more familiar. So KGL will be over C will be sent to little ku, not with the big K. Does it answer?
Still doesn't answer. So what's the very, I mean, effective,
Okay.
I mean, effective with respect to the slice.
Okay,
so
sorry, sorry. Effective.
Okay, that was the question, if it's the same thing, yeah.
Yes.
I have another stupid question, but does this KGL, small KGL, represent connective K-theory somehow? Connective K-theory in sense of Levin-Morel?
What? What can? What? Maybe Mark knows. I don't know what you mean. I mean, I know connective K-theory classically, but what do you mean by Levin-Morel?
Yeah, I think that's true, yeah. If you take the zero, if you take the, you know, the 2n part of kg, this little KGL, that gives you the connective K-theory as oriented cohomology in the geometric sense.
Yeah, so what you get from algebraic cobordism if you just tensor with Z beta.
Right, exactly.
Okay, thanks.
On smooth things.
Okay, so now with this in mind, we can formulate the main result precisely. So main statement, so that's due to us, and also employs, as I said, the recent work of Tom. The result is as follows. So there is an equivalence of symmetric monoidal infinity categories between KGL modules and this so motivic spectra with finite flat transfers, or like generalized cohomology theories with finite flat transfers, which so commutes with the forgetful map. So this means that the structure of a module over little KGL is the same as equivalent to a structure of finite flat transfers. And in this sense, little KGL is the universal generalized cohomology theory with finite flat transfers, which is almost correct, except that we only know how to prove it if you invert the characteristic in case it's positive. So E is the exponential characteristic, which is 1 if characteristic is 0, and P otherwise. Okay, so this is the main statement now formulated precisely. Let me write down the model again. Generalized motivic cohomology theory with finite flat transfers. Well, actually, every time I say flat, I should be saying locally free, but I hope you forgive me for that. Okay, so this is not at all the first result in this fashion. So you can, so the statement is analogous to the following statements which were proved previously. So since Tony asked about motivic cohomology, for motivic cohomology, there is an celebrated result that modules over motivic cohomology. Also, this is also known after inverting characteristic, are equivalently the Voevodsky's derived category of motives, which, so this is due to some of the organizers, I guess. So let's, yeah, find X Ostva, and oh no, that's not how you write this. Okay. And Hoyois Kelly. So, okay, here the right-hand side is denoted differently. It has different letters, but actually this is also the, can be constructed in the same way as a category with a different kind of transfers called Voevodsky's finite transfers. And similarly, so analogous statements holds for the Milne-Witt motivic cohomology and Milne-Witt motives. So that's due to Almanta and Kolderup. And again, you have to invert the characteristic. And the last but not the least, there is, so for algebraic cobordism, there is an equivalence between modules over algebraic cobordism, which actually holds over arbitrary base. So proudly write that. Since and you don't have to invert the characteristic, so that's a more general result. Where here you want to put, so not just finite flat transfers, but there is an additional condition of LCI, local complete intersection. So this says that motivic cohomology and Milne-Witt motivic cohomology and algebraic cobordism were previously proved to be universal with respect in term universal cohomology theories with some kind of transfers, and now we add little KGL, the effective Ktheory spectrum, to the list of cohomology theories with this nice property. Other questions before I will tell you some fun parts of the proof?
What does this have to do with other notions of universality for MGL as universal oriented theory? Is it exactly the same, or more restrictive, less restrictive, more precise, less precise?
You mean for algebraic cobordism? I think they're closely related, but I don't think so. This statement about MGL modules and your results about, results about MGL being.
No, it's not my results. It's, so there are universality theorems about MGL. Maybe Oliver.
Yeah. I already corrected myself. Oliver, Marcus, and Konstantin Pimenov. Yes, I don't think so. Their result certainly does not apply this statement, but also, yeah, it's in a similar direction, but a different result. I don't think any one of them applies the other.
Okay, thanks.
Can you give us a quick idea of why the finite flat SH model is connective in some way?
Why what?
I mean, why are you using the connective version of modules over KGL that indicates that you're looking at connective spectra, not connected spectra? And why does each finite flat have that property?
So, I mean, I think you could try to formulate a statement about the big KGL, so the non-connective,
Yeah.
in material sense. But so this will be obtained from this guy by inverting the Bott element. So maybe you could say that the actual Velitzky's Ktheory spectrum is universal with respect to finite flood transfers on which Bott acts invertibly. But I don't know how, so I can formulate this nicer for little KGL.
Thank you.
Okay, okay, don't worry, I won't give you the full proof, but I'll give some part which I find nice per se, so separately. But let me first say that, so the proof consists of 2 parts. And I will only talk about one of them. So the first part is to study the K-theory space as a motivic space, so which is by construction the infinite loop space of the little KGL. So this is, as we discussed, by definition, Zariski locally just group completion of vector bundles. And the main idea, the key idea, is that we prove that, so there is a forgetful map from the stack of finite flat schemes. So this is the stack of finite flat schemes. So I mean, that's a pre-sheaf which sends a scheme to the groupoid of finite flat schemes over it. And the forgetful map from finite flat to vec just forgets the multiplication. So this map forgets multiplication, then you get a vector bundle. And so the stack of finite flat schemes is also has a monoid structure by taking disjoint union. So you can also group complete it. So you have the forgetful map. Okay, so that's and the statement. So the key idea is that we show that this map is an A1 equivalence on affines. Actually, so all A1 equivalences in this talk will be on affines. I will probably not write it every time. So if you're not very familiar with this A1 equivalences business, I will say in 5 minutes, like I will show explicitly what does it mean. It will be a very explicit A1 equivalence. So, okay, this is nice. And we can also notice that this map, since it's just a forgetful map, which forgets a multiplication, it preserves all kinds of structures. So this is an A1 equivalence of, say, sheaves of spaces with all whatever structure they have, like infinity spaces or frame spaces, or like, let's say, spaces with finite flat transfers. And so why is it important? This means, so morally, this means that, well, this guy, the infinite P1 loop space of little KGL is, so since up to A1 equivalence, it's this thing. Can you see when I have it? Yeah, you can. Okay, so so we deduce that. So this is, as a metric space, the universal group-like A1 invariant Nisnevich sheaf with finite flat transfers. So basically, this means it says that the infinite loop space of the spectrum has the property that we want, and that's where the geometry, if I can call it this way, happens here. This equivalence. Okay. No, in the second part there is also geometry. Sorry, I shouldn't be saying this. What I want to say is that, so this first part is some explicit concrete statement about the comparison of these two motivic spaces, and the second part of the proof, which I want to skip, is how to deduce the main theorem about the comparison of KGL modules and SH finite flat. And this comparison uses a lot of general machinery. So what I was trying to say is that there's a big contrast that like this equivalence uses pretty much nothing, and the second part uses pretty much everything, you know. Concretely, this uses motivic recognition principle, which, okay, so if you know about it, then it allows you to deduce that little KGL is the frame suspension spectrum on the stack of finite flat schemes. But we won't talk about it today. And so this also employs the cancellation theorem for motivic spaces with finite flat transfers, which Tom has recently proved. So the statement is analogous to Voevodsky's original cancellation theorem for spaces with Voevodsky's transfers. And thanks to Tom, it also works for spaces with finite flat transfers. And okay, more stuff, let me not go into it. So I'd like to concentrate on the first part. Yeah. Questions? So, and I also told you in the beginning that we need to work over perfect field, but actually all the perfect field assumptions are only used in the second part, which employs, as I said, fundamental results in motivic theory. And in the first part, you use nothing. So the first part works over arbitrary base. Works over anything. Let's see. So the main ingredient. So I'd like to explain how to get this A1 equivalence, but along the way, we will prove a nice statement, which I like. I mean, it looks to me like it has a nice formulation and a simple, very simple proof. So I'd like to explain it. So the key ingredient is the following. So there's another way to connect the stacks of vector bundles and finite flat schemes, as in, so when you can look at vector bundles of some degree, say d-1, when d is at least 1. And you can consider the map to finite flat schemes of degree d, called, it's usually called a square zero extension. Which takes a vector bundle and sends it to O plus E, where here, so you take zero multiplication, because that's the only thing. I mean, since you don't have a multiplication, what else can you take? Okay, so that's a square zero extension map, and the theorem says that this map is an A1 equivalence. And so this I do want to prove. So you can define an A1 inverse by going back, by taking finite flat scheme or algebra if you wish, and sending it to the quotient by the unit. And so this will be our inverse map up to A1 equivalence. And so, okay, what does it mean that these two maps are A1 inverse? I want to argue that the two compositions are A1 homotopic to identity, and about one of them is just identity. So if you take a vector bundle and apply square zero extension and then quotient by the unit, you get back your vector bundle. So clearly one of the compositions is identity. So we want to show that the other composition is A1 homotopic to identity, so that the map from finite flat D to finite flat D, which sends A to A mod O plus O, that's not an isomorphism clearly, but we want to show that this is A1 homotopic to identity. So we want to like explicitly fiber it over A1 so that we see how it goes. And so there is a very simple, turned out that there is a very simple way to do it. Originally we had a more elegant proof, I think, but okay, it got simplified to being embarrassingly easy. So this employs the so-called rhys algebra construction. Which is as follows. So it's a general algebraic construction. So whenever you have any ring and any algebra with an increasing filtration, so let's see. Such that unit is in A0 and we want the product to satisfy the natural condition. So A is the union of AIs. So just an algebra with a natural increasing filtration. Then you can consider this rhys algebra, which is, okay, it lives in the polynomial ring over A. And you take polynomials that, so this eth coefficients is in degree I. So it's the graded, it's a graded S of T algebra. So what's nice about it for our purposes is that you can check by hands that if you quotient by the ideal generated by T, then you get the associated sum of graded quotients, so the sum of graded pieces. And if you quotient by the ideal T minus 1, then you get back A. And moreover, the last thing we want to use that if all graded pieces, so this AI mod I minus 1 are flat, or I mean finite flat, then so is the rhys algebra. Okay, so that's a very simple construction, and well, once you have it, if you already came up with this idea, then this gives you what you want straightforwardly. So we apply this construction. to the only canonical filtration that we will have on any algebra. So to the filtration. So given by the unit inside A. So this will be our A0 and this is A. So for any A finite flat. And okay, so then we get as I wrote above, we get that then this construction gives us the desired A1 homotopy, because instead when you quotient by T, you'll get this S plus A mod S, where here you have zero products, so zero multiplication. And if you quotient by T minus 1, you get back what you started. So this is a very functorial construction. So this map will gives us, so let me write it more explicitly. So it gives the map on stacks. So when I evaluate stacks like this, but it further extends to the actual map of stacks. So from A1 times 1 flat to n flat, which is the explicit A1 homotopy that we wanted. So maybe I've been going too slow because you seem to be silent because I'm telling you obvious things, but it took us very long to get to this super obvious thing. Between A goes to M and O plus O, and the identity. Okay, so that's the proof. Yeah.
So is this the part where you used to have like non-unital algebras and bank robbery and stuff like that?
That used to be, Tony, but now it got simplified to this embarrassing.
That's unfortunate.
No, okay, no, actually, not quite. So yeah, the bank robbery disappeared from the paper, and I'm very sad. But non-unital algebras do appear in the piece that I skip. So I hope this proof was understandable, because I mean it's very straightforward. But I wanted to say a couple more words on how this theorem, so this comparison, does not immediately necessarily imply what we wanted about the group completions. Let me say a couple words about this. And Tony, that's where the non-unital things appear, but I won't explain this. Yeah, so with this, this theorem allows, with some more effort, to prove that the forgetful map from finite flat to vect induces an equivalence after group completion. So that's it's a very different kind of map, because the square zero extension map does not preserve any structure like commutative monad or something. So it's not immediately obvious, but still you can use it to show this thing. And let me just mention a couple main ideas. So first of all, what does group completion have to do with any of the above? So you would use that group completion, which is a very abstract operation in general, up to A1 homotopy in this case. So for vector bundles up to A1 homotopy, this is something quite concrete. It's z times the telescope on vect. So this guy is column at of adding a trivial piece. So we are lucky in this A1 world that group completion is something concrete. And what we care about is the group completion of the stack of finite flat schemes, which also turns out to be, luckily, this telescope. So then if you want to compare group completions, it's enough to compare the telescopes on the right up to one homotopy. And and you would use then that, so as we showed above, we have this A1 homotopy given by the square zero extension, and square zero. And the forgetful map then in the composition gives you the just adding trivial line bundle. That's the composition. And this map is A1 homotopic to identity on the telescope of vector bundles. So if you believe my cheating, this is not an actual argument, this is cheating because it does not work as simply. But the main ideas are here. So you should think of it, I mean, you can think of it this way, that like this square zero A1 homotopy that we have just proved, combined with, I mean, the Siegel-Magdaf in motivic world, and this fact about the telescope sort of gives you the idea of why we get the statement about comparison of group completions, which preserves all the structure. So this is the story about the main theorem and its proof, or at least what I wanted to say. And I'd like to tell you also about some applications, but first I'd like to ask, are there more questions? No more questions? Okay. So some application, yeah?
So yeah, just does this result in the end have, maybe you're going to talk about this in applications, but does this clarify somehow relation between connective motivic cohomology and connective K-theory? That was asked already, but I remember, I mean, in terms of connective K-theory and the Chow ring in algebraic view through the geometric version, you have these extra relations that, you write the Chow ring is a quotient of connective K-theory, and the relations are of geometric nature. So is there anything like that here, where you can write motivic cohomology in some sense as a quotient of the connective K-theory by some geometric type relations? Or is that just saying you allow all finite transfers? Is that the idea?
Yes, so I mean, I wish I could, but I don't think I can deduce something about geometric relations, that what you're talking about. So what this, I mean, the story about KGL tells that, okay, motivic cohomology have more transfers, finite transfers are more, Vygotsky's finite transfers are more than just finite flat transfers.
But I guess what I mean is on the groups, if you take the end of the story, like you look at it in the degree 2nn,
yeah,
then rather than getting sort of a quotient in this homotopy theoretic sense, maybe it actually gives you a quotient on the group, on the individual group level. Any reason for that? That's the.
I'm not sure, but maybe, let's see, maybe towards the end you will get some kind of an answer.
Okay.
Not really, but
sorry for interrupting.
Let's get back to it in 10 minutes and see if it clarifies. So I would like to tell you about two applications. So one is something I've already told about many times, and the second one is something we observed recently, thanks to Tom's new result. So the first one is that we get a Hilbert scheme model for the motivic K-theory space. So for K as a motivic space. And we do this as follows. So as we saw.
Mura, may I disturb? Sorry for interrupting. There's a question in the chat.
Oh no, I was just trying to answer Mark's question.
Okay. Sorry. Sorry
Okay.
for interrupting again.
Yeah, sorry, I don't see the chat. So if you want to talk to me, please talk. I'm here. Okay. So let's get a Hilbert scheme model for K-theory. So how do we do that? We saw that K-theory is so Zariski locally the group completion of the stack of vector bundles, which is up to one equivalence, same as Z times the telescope and vector bundles. Okay, but there is this cool thing called the Hilbert scheme of infinite affine space, which is the central object of our studies, I guess, turned out to be. So this is, I'll define it. So this guy is the colimit of Hilbert schemes of an over n. And so it's a, okay, it's an int scheme, which as a functor of points can be defined by, it sends by sending a scheme T to the closed subschemes in A and T. So okay, I'm defining Hilbert of A here, but you can take colimit of these things, which is finite flat over T. So finite flat. And this has a forgetful map to the stack of finite flat schemes, which I mean just forgets the embedding into a finite space. So sends this thing to Z over T. And so the not hard to show effect, which we use all the time, is that this forgetful map is an A1 equivalence. So this should be read as, if you have a finite flat map, then it can be factored in different ways through a affine space, some affine space over the base, and you can factor it differently, but the space of all embeddings is A1 contractible when you let the dimension of a affine space go to infinity. So, I mean, that's believable and analogous to a statement, classical statement in topology. Space of embeddings into infinity is A1 contractible. Okay, and so, but very good. So we can play with this by replacing the stack of finite flat schemes with the Hilbert scheme. And so we get from our previous comparisons, from the comparison of the stack of vector bundles and finite flat schemes up to group completion, from the previous theorems, that then K-theory is A1 equivalent to the, so instead of taking group completion effect, I take group completion of finite flat and replace it with this Hilbert scheme. So, which is, I mean, the int scheme itself is not a monoid, but up to one homotopy, it is a monoid. So, monoid up to one homotopy, and I mean the monoid structure is you take the disjoint union of closed subschemes, and you can make them disjoint in the infinite affine space. Take disjoint union of closed subschemes in infinity. Okay, and and we did obtain also that you can do this telescope thing here too. So this is then A1 equivalent to Z times the telescope on the Hilbert scheme, where you like stabilize with respect to degree and the damage. So you get a Hilbert scheme model for Ktheory, which makes geometers quite happy because this allows you to, or allows us in the update to the paper, which will appear next week, say something, so we can then identify cohomology of the Hilbert scheme of infinite defined space, and also we prove stability results and say something about Hilbert schemes of finite defined space. So, but let's not get there. So that's another direction, like you can advertise it to geometers. And we also hope that in general, this story allows new approaches to some questions in motivic homotopy theory, which was already employed. For example, Eldon and Tom Bachmann have a preprint on a new approach to some of Vygotsky's conjectures about slices, or solved conjectures about slices, using this Hilbert scheme story. So, okay, that's nice. But the last piece of information which I want to tell, which is relatively new, is that you can generalize it to KGL homology of smooth proper schemes. So the idea is that we can more generally argue that for X, for a smooth proper scheme over a perfect field, we have a model for infinite loop space of KGL tensor X. So it's a space whose homotopy groups are given by KGL homology of X. And so we get that it's motivically equivalent to the group completion of the Hilbert scheme of infinite defined space over X, which is again an infinite space via disjointinian. So this also uses Tom's work. Same work, same recent paper. And so this is true for any smooth schemes if you invert characteristic, but for smooth proper schemes you don't need to invert characteristic. And this, we believe, this is some approximation to an analog of Siegel's results for classical KU homology. So it's somewhat. Oh, Mark, are you still here? I wanted to say that some kind of a not really answer to your question would be that so having this, the canonical map to motivic homology so this equivalence is compatible with the Hilbert-Chow map to symmetric powers on the right-hand side. So this gives you some geometric interpretation of the map from KGL to HZ tensor X. But I guess that's not what you wanted, but it's still something.
Close enough.
Thank you. But I wanted to say explain the very last thing, that we believe it's some kind of analog to Siegel's model for classical little KU homology. Because, so what Siegel showed is that infinite loop space of KU tensor suspension spectrum on a space. So what people consider in the classical story, he showed that this is weakly equivalent to the group completion of the so-called labeled configuration space of X. Oh, one thing I learned from writing this paper is that labeled has less L than I always write. Configuration space of X, which is, so it's a space, the space, so it's an infinity space whose points are tuples of points of X labeled by vector spaces. Well, in this case for KU, complex vector spaces which are pairwise orthogonal and embedded into C infinity so that you can define an infinity structure. Points are tuples of points, of points of X labeled by pairwise orthogonal complex vector spaces embedded into C infinity so that you could define it as an infinity space. And so, okay, so this looks kind of different. I mean, what does it have to do with the Hilbert scheme? And we argue that it has something to do with the Hilbert scheme because, so we want to say that this Hilbert scheme of infinity-defined space over X is some kind of a geometric analog of this labeled configuration space up to on homotopy, because what we have is that we have the so-called Hilbert-Chow morphism from the Hilbert scheme to symmetric powers, which, so it's called Hilbert-Chow. But so morally, it looks at this like points on a scheme as a closed subscheme, but it only remembers the support of the points and the degree and nothing else. So it forgets the geometric information, except for support and degree. And then you can project to symmetric powers of, on X. I mean, sorry, symmetric powers are just scheme parameterizing tuples of points on a scheme of any amount. So of fixed degree, there will be d tuples, and when I don't write degree, so any degree. So this is a forgetful map. So our Hilbert scheme has a forgetful map to the tuples of points. And I want to say why this can be thought of as some labeling with vector spaces. And the idea is that we show that if by similar methods, what I explained above, that a fiber of this map over a k point in the symmetric powers over, say, so sum of ai pi, where pi are k points, distinct k points. So this fiber is motivic equivalent to the product of stacks of vector bundles of some degrees. So we fiber our Hilbert scheme over the symmetric powers, and the fibers are even equivalent to products of vector bundles. So in some sense, it's analogous. This is not a very precise analogy. For example, yeah, okay. So we want to improve it and to get a better model, but currently this is already something. And the last sentence of my talk is that I'd like to emphasize that, so we get in this story, we get a geometric model for any smooth proper scheme. In particular, it makes sense to plug in the projective line or I don't know, PN, something like that. And so we get a geometric model for its little k homology. And the cool thing is that this equivalence holds without inverting the characteristic. So also add the positive characteristic. And the big dream would be to use, so let me write this since it's a talk. So big dream, which we won't get to, but maybe some of the people at this talk can, is that you can use that if you quotient little kgl by the by beta, by the bot element, get motivic homology. And the big abstraction in computing, say, motivic standard algebra at the characteristic is that for higher spaces of motivic homology, you only have a geometric model given in terms of symmetric powers up to inverting the characteristic, so not at the positive characteristic. And here you see this thing holds also at the positive characteristic. So in case someone knows how to compute cohomology of the Hilbert scheme over projective space, for example, maybe those people can, compute motivic standard algebra at the positive characteristic and solve all the remaining problems in motivic homology. That's the spirit. Thank you for your attention, and please ask more questions.
Yeah, thank you very much for this beautiful talk. Thank you, Una. Are there any? Let's thank the speaker first. And let's get to further questions, if there are any.
Why proper?
Because of this.
I mean, it's homology. It shouldn't care whether the X is proper or not. I mean, I
mean,
I see.
So this inverting characteristic business happens in all these modular results because not proper schemes generate the whole thing after you invert characteristic. So this is the issue happening every time.
Really?
Yeah.
I mean, if X is not proper, don't you?
I have to invert the characteristic for this to be true.
Really? Ah, you mean, but it's true if you invert the characteristic for non-proper X.
Yeah.
Ah.
Yeah.
Okay, but it should be, I see, it's a technical question though. It's a technical issue.
Well, yes, but it's a big issue. I mean,
sure. I'm just, okay, but philosophically it shouldn't be there is what I'm suggesting.
I would be more careful because for symmetric powers, for example, at the positive so symmetric powers in a similar way.
Yeah, but these are not symmetric powers. This is
yes,
the
but since it's wrong for symmetric powers at the characteristic, I would not dare to claim that it's true here. So I don't have a counterexample, but I don't know if it's before you invert the characteristic.
Oh, okay.
When you write Hilbert the infinity, you mean the Hilbert scheme of finite flat things?
Yes,
or do you mean
points. Mm-hmm.
Okay.
Laura, there's also a question in the chat.
Oh gosh. So big KGL is little KGL when you invert the bot element. So you periodize it. Little KGL is connective and big KGL is not. That's the answer to one question. Labeled is fine. Why my co-authors correct my labeled every time? Okay, thank you. What else?
Well, you don't have to read the whole chat now. You can later. There were some discussions. So other further questions?
Yeah, sure. Well, maybe this is more of a remark, but so this suggests that maybe there should be some cobordism type models for connective K-theory. And perhaps, I mean, interesting thing would be to construct a non-A1 invariant geometric connective K-theory. And
yes, very much so. And I heard that you have a business on that doing for MGL and other things.
Yeah, exactly. But I mean, the problem is that for cobordism, it's very hard because it's hard to understand the right schemes, especially the types that get used. But maybe it's easier to understand connective K-theory. For example, maybe it's easier to prove localization kind of theorems and so on. I don't know.
I mean, maybe we only, I mean, my crew only tried to do this for algebraic cobordism and we got stuck. And we now hear rumors that you're making more programs on this. So maybe, but like, let's try to talk about it later. I mean, there is a hope that it will be more doable, but it's still hard. So it requires discussing. So I wrote to Tony and I meant to write in the chat that yes, there was a question about HZ being the killing bot element in KGL. Yeah, that's true. And was there?
Yeah, are there any further questions?
When you say compute the motivic Steenrod algebra, do you mean the unstable operations or what? Because Voevodsky told us what the stable Steenrod operations are.
I mean, to do whatever is done only when you invert the characteristic. So I guess unstable. So I mean, I'm not sure. Well, I think there's a famous problem in motivic homotopy theory, which is related to also Hopkins-Morel Hoyois isomorphism only after inverting characteristic and other things. Right? I mean, some of the organizers have been thinking about it for years.
Okay, if there are no further questions.
Oh, one last, wait, before you go. I'm not going to give up on this inverting the characteristic business, because you're saying, well, it's a problem because there's a problem with symmetric powers, but there's also a problem with symmetric powers even with X smooth and proper. It's also false for X.
Oh, you're right. Yes, Mark. I'm not. You're right. I don't have a proof that it's a problem.
No, I'm not asking for a proof. I mean,
yes.
I'm asking for a reason.
Yes, you're right.
You still haven't given me a reason, is what I'm saying.
Yes, I have not given you a reason. You're right.
Okay. Good. Still hope.
You win.
Okay, one last. What if you assume resolution of singularities? Does that help?
Let me check and tell you later again.
Okay, thanks. I'll be quiet now. Thank you.
You're welcome to ask more questions, Mark, and anyone else also, but only for a very few seconds before we thank Murat again. Next talk will take place 5 o'clock Oslo time. See you then.